I would like to thank you all for letting me speak here, and thank the organizers for, thank the organizers for letting me speak here, and thank the people who are attending for attending. I'm almost the last speaker, so I'd like to thank the previous speakers for making this a really stimulating and interesting conference. Okay, so what I'm going to talk about is work that was originally motivated by a physics question and then took on a mathematical life of its own. The results I'll talk about date back to about 10 years ago in joint work with Stanley, and then more recently with Chi-Dong He, who is an exceptional undergraduate at Colby and is now a graduate student at Rutgers. My sharing is paused again.
Yes, it's paused. Now it should be okay, I think.
Yes,
it's okay.
So I'm going to talk about two numbers that are associated with Lie groups. And for these purposes, we're going to talk about Lie groups. Think of them as metric groups in the standard representation, which is the smallest faithful representation they have. The first number is NGM, which is the number of conjugacy classes of elements of order dividing M, which is all elements X in your group, such that X to the M is 1, and we're looking at the conjugacy classes of those. The second number looks at the same conjugacy classes, but classifies them according to how many distinct eigenvalues they have in that standard representation. So one thing to easily notice is that if you sum your NGMS over S, you get N of GM. So what I'm going to do in this talk is I'll talk about these two numbers for the whole talk. I'm going to start with a simple example, then I'll talk about the motivation so you get a flavor of what physics led to this, and then I'll talk about as many of the results as I have time for. So let's think about the unitary matrices. We all know that we can conjugate a unitary matrix to a diagonal matrix, and that means that every conjugacy class in the unitary group meets a diagonal element. That means that if you're going to count conjugacy classes, we can think about the diagonal matrices only, and we don't have to think about the entire unitary group. Now, what does a diagonal unitary matrix that has order that divides M look like? Well, it's going to have eigenvalues, which are nth roots of unity. Now, it's also the case that if you permute the diagonal entries, you can obtain that action by conjugation. And so we can restrict what we're looking at to diagonal matrices for which the Ks are non-decreasing. And then we can pretty easily compute this. So N of U and M is just weak M compositions of N. And then if we do this by number of eigenvalues, then we pick the S eigenvalues first, so that's M choose S, and then we divvy them up to the N positions along the diagonal, and we get this rather pleasing expression. So where did all that come from? So the original motivation came from symmetry breaking in M theory. I'm not going to define M theory or string theory here. I'm just going to give a flavor of where this is coming from. So physics has symmetries known as gauge groups, which are described by Lie groups. There are several popular ones like SUN or SON. A common theme is breaking a symmetry to a subgroup. And that subgroup, in the context I'm talking about, is the centralizer of an element of the bigger Lie group. For example, if you start with a grand unified group of SU5 and you want to break it down to the standard model of particle physics, which is this subgroup, one way to do that is to take an element in SU5 that has order M, and I'll tell you a little bit in a moment where M comes from. You have two blocks here on the diagonal, and if you think about the commutator of this matrix gamma, you're going to see that you get this subgroup. So that's a sort of classic example. And the very original example that I worked on was a little more general. It started with SUN, broken down to a bunch of SUNs and a bunch of U1s. In the physics, the number of U1 factors here corresponded to the number of photon-like particles in the remaining gauge theory, which is physically important. And the number of ways you could get from SUN to such a subgroup is the number that we were interested in. It's the number of vacua, and it's the number of diagonal elements in SUN whose centralizer is exactly this group. Now, in string or M theory, as you know, or you've heard, we have extra dimensions. When the extra dimensions look like a lens space, S3 mod ZM, then it's exactly this number that I defined at the beginning, N of SUN MS, that gives the number of vacua, which is why I started computing this in the first place. So well, I'm not going to do a lot of details, but give you just a flavor of this. So if we want to count diagonal matrices in SUN, which have order dividing M, then the eigenvalues are nth roots of unity. If this particular eigenvalue with K up here appears NK times, then what we're looking for is sets NK that sum to N satisfy the determinant condition for the special unitary group, and exactly N of the SKs are not zero. Now, when M and N are relatively prime, which is actually a condition that comes from the physics, believe it or not, you get a really beautiful simplification that gives you this expression, which I obtained way back in my PhD in string theory. If you notice the result for the UN without the S, you'll notice that this is just 1 over M of that. The reason is that this determinant condition, 1 of M of the diagonal matrices we look at, gives you 0, so we divide by M. So then I got my courage up one day and walked into Richard Stanley's office, and I asked him, do you think we can count this for other Lie groups? And he said, why not? So here we were. We got the computation for SUN when M and N were not relatively prime. Orthogonal and symplectic groups had similar sort of relatively basic computations with very interesting subtleties that came up, especially when questions about whether M is even or odd, when the orthogonal groups are even or odd, or connected or not connected. In all cases, we use the torus theorem to count things in the torus instead of G. The analog here of the torus is just the diagonal matrices of UN, and there's a torus for the other Lie groups. As we were doing this, we learned that Djokovic in the 1980s looked at one of these two numbers, N of GM, but not N of GMS. He had no motivation for that. The motivation for looking at S came from the physics. So here are all the results from a paper with Stanley, and I'm not going to go over the details. There's a relatively small overlap with Djokovic's work here. He didn't consider all of these groups. And then this column is completely new, and you can look at it, and I think it's a rather pleasing set of formulas. So notice that we're doing here only classical Lie groups. We decided to leave exceptional Lie groups for another day. That day came some years later when a student at Colby asked me for a project, and I thought, let's try this counting for G2. The summary of what results we have is that we have results for NGM in closed form for all the exceptional groups, and we get this in a different way from what Djokovic had. We have N of GMS. We have an algorithm for getting N of GMS for all G, and the computer gave us nice closed forms for G2 and F4, but crashed for the others. Now, the approach we took was making good use of the wild group action on the torus. When I was working on the classical groups, I didn't even have to know there was a wild group. All the computations didn't use it, but this was useful for the exceptional ones. So there's a really useful theorem that says that if two elements of the torus are conjugate in a Lie group, then there's an element of the wild group that takes one to the other. That means that counting conjugacy classes really means counting orbits of the wild group in the torus. So the main ingredients here are looking at elements of the group whose order divides M, so X to the M equals 1. Those are always conjugate to some element in the torus. And then we used Burnside's lemma, but modified it. So here's our counting theorem. So here's some notation. We need to look at the conjugacy classes in the while group. We need a representative for each conjugacy class. And now we need to look at the fixed points, which is what Burnside's lemma tells us to do. We have T of Gm, which is all the elements in the torus that have order dividing M. And this fixed of WC is the number of fixed points in the torus under the action of the while group. And then T sub S of Gm is the subset of the torus of elements of order dividing M that has exactly S distinct eigenvalues. Burnside's lemma directly would have just given us a sum over the entire while group here. It turned out for our case that if two elements in the while group are conjugate to each other, then the number of fixed points in the torus is the same. So we just need to sum over conjugacy classes, which is a big simplification. So let me tell you a little bit about what happens with G2, which is the smallest example. The smallest Faithful representation of G2 is 7-dimensional. And now we need to see what a typical torus element is and how the while group acts on it. It's not as easy to find this as it is for the classical groups, which you can find in any old textbook, but we're lucky to find a paper by Howlett, Rylance, and Taylor that actually gives us torus elements for all the exceptional groups. So here's what a torus element looks like for G2. It turns out that the first two diagonal entries determine the rest of them, so we only need to really look at those. And here are the generators of the while group. And so what we're going to want to do is figure out when an element in the torus is fixed by an element in the while group. Now, remember, we're looking at elements of order dividing M, so these Ks here are going to have to be in Z mod M, or in 1 over MZ mod Z. Okay, so how do we do this? Here's an example. So here's an element in the while group. In blue, I have an element in the torus. In red, I have the element in the torus after the action of the while element, which is conjugation also. We equate the first two entries to pick out the fixed, the tori element that are fixed. And that gives us equations in the Ks. We get a 2x2 system. And we want to find the solutions, solutions in K in 1 over MZ mod Z for this system. So how many are there? This brings us to the Smith normal form. So this is a matrix from the previous page. The Smith normal form is this one. And remember, the Smith normal form takes your matrix, does the row reduction that you would teach in your linear algebra class, but does it over the integers. That part preserves your solutions. And then it also permutes, it reduces over the columns, does column reduction. That action does not preserve the solutions, but it preserves the number of solutions, which is all we want. So the number of solutions to the equation we were looking at initially is the number of solutions to this one where we replaced our matrix by the Smith normal form. And then this is pretty easy to read off. You have the greatest common divisor of 1 in M times the greatest common divisor of 3 in M. And so the answer depends on M mod 3. So we must do this for every conjugacy class, but there aren't that many conjugacy classes. One of the nice things about this is that for all the while groups, the number of conjugacy classes is not crazy big, while the while group itself could be much bigger. So here's the number of fixed points for every representative of every conjugacy class of the while group. And we plug this into our original counting theorem and obtain some tables. So for G2, the table depends on M mod 6 because, let me go back for a second. Here you see the elementary divisors in the Smith normal form. Here we have 1 and 3. Here we've got 2. The least common multiple of those is what's going to appear up here. So here are the results for G2, F4, and E6. We have them for E7 and E8. I just didn't put them on the slide. In the few seconds I have left, I'll talk about the second number, where we need to count, figure out when an element in the torus has S distinct eigenvalues, and how many of those are fixed by an element in the Weil group. This is far more involved and wouldn't be able to explain it in detail. Anyway, the general approach was introducing a set of matrices with a post-it structure that allows us to detect when eigenvalues are repeated, and then to count the number of elements that are fixed. So this is what the result looks like for G2. For F4, the table is much bigger, but the computer still did it. And the others, the computer crashed. So sorry about that. So I've basically told you what the results are. Stay tuned for studying the same numbers for matrix groups over finite fields, which I'm working on right now. So thank you very much.